we're closing out this chapter with least squares and fitting data. This is an important application, and it uses a lot of the ideas we have been building up in the past few days. So let's start with something that we touched on the first week of class, which is the following. You have an n by m matrix, and for some vector b in our n, the system ax equals b may have no solution. Okay, this is an inconsistent system, and we have certainly seen, and we'll see more today, times when this exists. Okay, but here is the question, is what we want. So question, how do we find, and I'll put this in quotes, almost solution? I'll call it x star question mark. And this is really the whole topic of today, okay? When you have some inconsistent system, what can you do? You have this coming from data, say, right? Fitting data, what can you do, right? I'm going to start with the definition, then I'll answer the question, and I'll do an example, but it's not going to be obvious that my answer initially is the right answer, and we'll come back and talk about that. So first of all, before I answer, let me give a definition. A vector, I'll put a star. This will be in, let's see, Rm is called, pardon me, it's called a least squares solution to ax equals b, provided, well, this is something I touched on a few videos ago about how do you measure how far one vector is from another. This b minus ax star, this length is less than or equal to the length of b minus ax for all x in Rm. So we're finding this vector in Rm such that this length, the difference between a times x star and b, is as small as it can possibly be. Now, if we have a consistent system, as we do many times, well, then there's either one or infinitely many solutions to this, and you take the one or the infinitely many, and they satisfy that this number here is 0. Okay, you can't get a length smaller than 0. So in effect, when you're in the consistent world, this new definition of a least squares, I'll also underline solution, is exactly what you're used to. It's just a solution to the linear system. But when you're inconsistent, this is what is the new idea. Now, let me give you, as I mentioned, I was going to tell you the answer, even though initially it's not going to make sense as to why this is the answer. But the answer, so you want to, instead of solving ax equals b, well, because we can't, because it's inconsistent, let's just multiply by a transpose and solve, well, the system, which is a transpose ax is a transpose b. And then I'll say a solution to this linear system, I'll just say system, is a least squares solution. Now, I hope you are as curious or wondering, and not just taking my word for it, as I hope you are, because if you see this, why in the world is that even consistent? okay, this system. Or why in the world would a solution of this be satisfying something like this? Okay, well, this we will discuss. And that's a really fun part of today. But first, I will just say this is always consistent. Okay, but before I get into the theory as to why doing this works, let us look at an example. Well, here's our first example, and it's even a fitting data type problem. We're given 3 points in the plane, 0, 3, 1, minus 1, and 2, 0, and we want to find the closest or best fit line to these 3 points, and we know that there's not an answer as to an exact line because these 3 points do not lie on a straight line, for example. But if we turn this into a linear system, this is similar to stuff we did at the beginning of this semester, maybe section 1.1, 1.2, something like that. Well, here is what a line looks like. And if I just evaluate, maybe I'll do this in blue. When I evaluate this at 0, I get 3 is C0. When I evaluate at 1, oops, I get that negative 1 is C0 plus C1, and then I evaluate at 2, and I get 0 is C0 plus 2C1. Okay, so let's write down our matrix. Coefficient matrix comes from this side as 1, 1, 1, 0, 1, 2, and this is A. Maybe I'll write that underneath. And then the vector B we see over here. 3, minus 1, 0. This is B. Now, you can certainly form the augmented matrix with A, augment it with B, and then perform elementary row operations, and you will realize this is an inconsistent system. However, I just realized it geometrically, looking at the 3 points, and there is no line that passes through all 3. Okay, is we want to solve the following. We want to solve A times C1, C2 equals B. And I mentioned it's inconsistent. Well, I told you the answer. I told you what we're going to do. We're going to multiply both sides by A transpose and solve that system. Okay, A transpose. This column becomes the first row, and the next column becomes this row. Oh, maybe I should just go ahead and write A transpose A. I'll do this right here. A transpose A. This will be 2 by 2. We get 3, and then we have 3, 3, 5. Okay, then we need A transpose B, because this is what we're doing. Multiply both sides of the equation by A transpose. So this will be 1, 0, 1, 1, 1, 2 times the vector B, 3, minus 1, 0. Okay, now we know there's a few ways we can multiply matrix times vector. It might be easier here just to think it's 3 times the first column minus 1 times the second, linear combination of the columns of A transpose. And when I do that, here I get 3 minus 1, and here I get 0 minus 1. Okay, so now the system that we would like to solve is the following. We would like to solve this system. 3, 3, 3, 5, C1, C2 is 2 minus 1. Now before I do anything else, we know immediately this is going to have a unique solution in this case because we only have here 2 columns to think about in this matrix, and this one is not a multiple of this one. So you know the rank, for example, of A transpose A is 2, and so you're going to have a unique solution here. Okay, so we have 2 options. Okay, these are good to talk about, right? This is a nice review of things we have done. You have 2 options. Number 1, you make the augmented matrix with this and this row reduce until you have your solution. Number 2, well, you can just find the inverse, right? I think I'm going to do that because it's 2 by 2, and it's very easy to find the inverse of a 2 by 2 matrix. And then multiply, you will have C1, C2 is the inverse of this matrix times this vector. Now, of course, that is not an actual solution to this because, well, look at the picture. This point do not lie on a line. But what we will find is it's the best fit line. Okay, so let's do this here. I have space. 3, 3, 3, 5. Inverse. Okay, we take 1 over. We take this minus this. This is 15 minus 9. And then you interchange the diagonals. You take negative of the off diagonals. And this is the matrix. Now, let's see where I can erase. The least squares solution, although I haven't justified that yet, this x star, this, well, we can solve for it. Maybe I should do that here. We'd get 1 over 6, this matrix, times here. Okay, well now we just have to do this, and we will have x star, and then we will look at it in the picture. We're going to talk about this, the length of b minus ax star in this example too. Okay, great. So what do we get here? Well, first I'll write the 1/6 out in front. So we have 10 plus 3. We have minus 6 minus 3. 13 over 6, and okay, well, now let me erase all of this because we have used it. Now let's write the polynomial, and we will talk about the error part of this because it's not polynomial. Well, it is a polynomial. I meant to say let's write the line. We'll do a quadratic at the end of today, but right now it's a line. Okay, so the line is y is 13 over 6 minus 3/2 t. Now just to kind of plot this, what are 2 points on this line? Well, the easiest one to see is 0, 13 over 6, which is about 2 1/6. And then if, for instance, I put 2 in here, this would be, now I'm going to have to do a little side work. If I evaluate this at 2, I get 13 over 6 minus 3, which is negative 5 over 6. Okay. So the other point on my line is 2 comma negative 5 over 6. Now let's just plot. I'll erase this side work. I tend to mess up fractions if I don't write them down. That's why I did that. So let's plot these 2 points. 0 is about 2 1/6. and then 2 and negative 5/6, something like this. Okay. Okay, now, let's get back to something that I mentioned at the beginning, which was the definition of the least squares solution. So what is this here? We have to, now sadly I have erased some things in this problem, but what we want to consider is this, b minus ax star. And I literally don't have b and I don't have a on the board anymore. Okay, this is why I'm going to go back to my notes. B was 3 minus 1, 0, and a was 1, 1, 1, 0, 1, 2, and then we multiply by this 13 over 6 minus 3 over 2. Okay, so let's compute this. I think I'm going to do it in 2 steps. I will write this one, 3 minus 1, 0, and then I will take this matrix times vector, and then I will take the difference. So I'm going to do it in 2 steps. Okay, here I have, now here's where I start to get nervous. No, I'm kidding. I'm okay. It's just fractions. We're going to make it. So here is where I have, well, the first one's easy. It's 13 over 6. You see, 13 over 6 is all this one is. Now the second one is 13 over 6. This is where I'm going to write some side work. 13 over 6 minus 3/2, which is going to give us 4 over 6. So this is going to be minus, it's a 2 over 3. And then the last one, we have 13 over 6 minus 3. Oh, we calculated this one already. This was minus 18 over 6, negative 5 over 6. Okay, very nice. That wasn't too bad. Negative 5 over 6. So this is the vector A times x star. Now let us, well, I'll erase this because I'll probably use it for something else. Now I will just take the difference of these two. Okay, this is 18 over 6 minus 13, 5 over 6. This is going to be minus 5/3, and this one is going to be a positive 5/6. Okay, this is the vector. What does this represent in the picture? And this is important. Here's the first component. How did we get this? It came from this point. This is the second component. It came from this point in our original linear system, right? This first row of A came from this point, and the second row of A came from this point, and the third row of A came from this point, and these also, what is this? 5/6. It is exactly this length, right? Because this was 2 1/6, and this is 3. So this length here is this first component, 5/6. And minus 5/3, well, I'll do that one last. Here's another 5/6, is this. Look, this is the point 2 comma negative 5/6, and this is right at the axis. So this length, 5/6. And now finally, minus 5/3, it goes from here. Now, why is it negative? Well, look, this is actual point, and this was the x star, right? Because it's b minus ax star, and this is the y values of b, right? And then this one is the y values of ax star. Okay, so this difference, well, it's negative because b, the the y value is less than here for that point. So this is what corresponds to the negative 5/3. Okay, so what we're doing here, well now, okay, let's talk about the length. And this is what we refer to as the error. You see, the components that we found in this b minus ax, in absolute value at least, they're the lengths of the vertical bars to sort of measure how far apart we are. And the error is what we're trying to, which we're trying to minimize. In this case, it's a square root of okay, I'll put the negative, doesn't matter, like this. And here's where I'm just going to look and see what I got. It's square root of 150 over 36. It's approximately 2.04. But one reason that people will call it least squares is because to find this being minimal, this length, is equivalent to minimizing the squares here underneath, right? The length squared is the sum of squares, or the sum of the squares of these bars. It's really what we're minimizing here. Okay, well, this is our first example, and it came to us from data fitting. I think it was a good way to begin. Now I want to go back and talk about why this method works and what we're actually getting here with this a x star. Well, what I mentioned is the answer is actually a theorem, and this is what we're going to talk about now. It says the least squares solutions to ax equals b are the solutions of the system A transpose A times X is A transpose times B. And this has a name. This here is called the normal equation. Well, it's the normal equation of this system, okay? Now, we have a lot to discuss about this theorem and why it holds and things like this. Before I do, or as I do, I should say, because we're starting to discuss it right now, what we really need to do is back up just a little bit. Right now, my comment, I'm making a comment number 1, and I've got several comments to make to understand why this is the case. The first comment is that the normal equation is always consistent. Let's talk about why right now. But first I have to back up, as I said. And the backup is to talk about, we're going to go back and spend a little bit of time with orthogonal complements. Okay. Well, let's suppose A is n by m. We have these subspaces, the image of A. We have the kernel of A. And then we have just been discussing the transpose. This is going to be m by n, and it has its own image and its own kernel because it too is a matrix. Now let's see where all of these live. What's the image of A? Is the subspace where you take the columns of A and you take their span. Well, we have m columns. Each is a vector in Rn. And so the image of A, I'm going to write it as subset, although we know all 4 of these are subspaces. This is in Rn. The kernel of A, what was this? This was every vector such that a times x is 0. Well, in order for a times x to be defined, x must be in Rm. So this sits inside Rm. Okay, now let's do the same thing over here. A transpose. Well, okay, again, now the image of A transpose. We're going to take all columns of A transpose, their span. Oh, that's going to be the image of A transpose. But now we have in columns, each of them is in Rm. So this is a subspace, even though, as I mentioned, I'm going to write subset of Rm. And then the kernel of A transpose, this is every vector such that A transpose times x equals 0. Well, in order for A transpose times x to be something, x must be in Rn. So this is inside Rn. But there's a lot more relationships than just locations. The most important one I will mention now, and we will discuss why. I'm going to call it a theorem, and we will prove it. Maybe I'll do it in red. If you take the image of A and you take its orthogonal complement, this will be the kernel of A transpose. So it's not just the case that this subspace and this subspace just happen to both be sitting inside Rn. It's more. It's that they're all orthogonal complements to each other. And this only says that the orthogonal complement of the image of A is the kernel of A transpose, but for instance, if you wanted the orthogonal complement of this, you would take the orthogonal complement here, and if you do it twice, you would get back the image. So this subspace and this subspace are orthogonal complements of each other. And similarly, I mean, if you now look at A transpose as being your matrix, if you took the orthogonal complement of this image, you would get here, okay? But I really want to talk about this one. And then, okay, we'll keep going. So why is this the case? I need to prove that these two are equal. Fortunately, I know that they're living inside the same place, so at least that has me started down the right path, right? So here we go. Let's prove this. I'm going to have a big string of if and only ifs here to show that in fact these two are equal. So x is in the image of A perp if and only if. Uh-oh, I'm not ready to start. Well, I need to give myself some columns of A, because what is the image of A? As I said, you take the span of all the columns of A. So before I start proving this, let's say that A, how many columns do we have? M of them. It's going to be V1, V2 to Vm, and these are columns, columns, columns. Okay. Now I'm ready to begin. Okay. Now, this I have discussed. Well, we know, okay, let me say one more thing. We know it's in this provided if you take the dot product of x and anything in the image of A, you get 0, right? But this collection is a spanning set. V1 through Vm spans all of A, all of the image of A. And so, being orthogonal or perpendicular to every single vector in a subspace is equivalent to being orthogonal or perpendicular to every single vector in a spanning set. Okay? So I'm going to say if and only if x dot v1 equals x dot v2 all the way to x dot vm m is 0. That's the number 0. Dot product of two vectors gives you 0. Well, if and only if, now I'm just going to put these as rows. This is going to be V1 transpose. Then I'm just going to go down to the mth. VM transpose. Okay. Then these are now rows. Row, row. This times x equals the 0 vector because what is this times this? Well, you take row dot x, row dot x, row dot x. So if these dot products are all 0, or these dot, I should say it as an if and only if, these dot products are all 0, if and only if this matrix times x is the 0 vector. But if you look at this matrix for 2 seconds, maybe 5, 10, I don't know, you will realize this is a transpose. Okay, so that says if and only if x is in the kernel of a transpose. And that is the end of the proof of the theorem. These were all if and only ifs. And so it shows that the image of a orthogonal complement, excuse me, is equal to the kernel of a transpose. So I have taught this course from other textbooks than ours. And some other textbooks will call these 4 subspaces, the 4 subspaces of a matrix. And spend a lot of time talking about that because it's a really fundamental thing to linear algebra. But what our discussion has shown is that these two are orthogonal complements. Okay? In fact, that's the one that I proved. But as I mentioned, similarly, these two are orthogonal complements. Okay? Okay, well, now let's go back to this, right? Because remember what we're trying to do? Least squares solutions. Okay, next, here we go. I'm still trying to talk about why the normal equation is always consistent. And this one we will get to momentarily. But let's talk about this. So AX equals B, inconsistent. In the language of what we just discussed, this means that B is not in the image of A. Now, why is this? Well, A times X you can always think about as linear combination of columns of A. So in particular, any vector of the form A times X is without a doubt in the image of A because, well, it is a linear combination of a spanning set, which is the columns of A. Okay, so if this is inconsistent, then B is not in the image of A. Now let me just draw, I'll say one more thing, and then I'll draw a picture. Then this is the closest vector to B that is in the image of A. Now let's draw a picture. So how can I get this closest vector to B that's in a subspace? Well, we have been doing this the whole chapter, but I'm going to draw a picture that is it's going to be a two-dimensional picture. My subspace, though, is only going to be one-dimensional. Okay, let's suppose this is the image of A. Okay, that means that I must have 0 somewhere. Very nice. Now, then I have a vector. This is a one-dimensional subspace in my picture. Then I have a vector that is not in the image of A. Okay, here we go. Here's B. Okay? How am I going to find the closest vector in this subspace to B? Look, What are you going to do? Just do this. And then here's the answer. This green is the closest vector to x that is in, I'm sorry, the closest vector to b, this one, that is in the image. But what is this? This is the projection. So we get, so then this ax star is the projection onto the subspace, the image of A, of the vector B. Okay, well, we're using, this is why this is the last section in this chapter, because we've already used orthogonal complement, we've already used transpose, and now we're using projections. Okay, so we using all the ideas from this chapter. It's quite a beautiful end to the last handful of videos. Here we go. Now, okay, so then we continue. If I take this, so this is now, so I'm projecting B, so this would be, well, it's this. Well, you take the vector B minus the projection. We know, well, let's draw it on the picture. I'll do this one in black. It's this one. This vector is perpendicular or orthogonal to the subspace, which means, okay, is in the image of A perp, this orthogonal complement. But what's the orthogonal complement? This was our backup discussion. This is equal to the kernel of A transpose. Okay, so now we just keep unraveling this a little bit more. Now I'm just going to, so this vector here, look, this vector here is in the kernel of A transpose. So if I take A transpose times this vector, I get 0. Okay, so we have rearranging if you multiply and rearrange, we get A transpose B equals A transpose A times this vector. You see a few things here. Number one, the least squares solution really comes from projection. And then we see that minimizing the length B minus AX star is really equivalent to solving the normal equation. Finally, we see the normal equation is in fact consistent. My next comment has to do, or this is comment 2. After this comment, I'm going to get back to more examples. But this is also an important one. And it has to do with the case when the columns of A are linearly independent, or when they do form a basis for the image. So the columns of A form a basis for the image if and only if V1, there's a few ways to say it, and I will mention a few, are linearly independent. We already know they span. We could also say if and only if the rank of A is M, the number of columns. Another way to say this, and this would be through the rank nullity theorem we discussed. This would say that the kernel of A is 0. So So there's a few ways to say all of this, but in this case, and this is what I want to talk about, in this case, the kernel of A transpose A is also 0, and A transpose A is square. Let's think about that, right? Because this is what we're solving. I left it on the board. We're trying to solve. I can also write it this way. Well, okay, fine. And this is a square. In our example, we saw it was 2 by 2. And if this is kernel 0 and square, invertible, which means we can solve this system just by multiplying by A transpose A inverse on both sides, as I did in the example. Proof. Okay, well, how am I going to show this is 0? What I'm going to do is I'm going to let x be in of A transpose A, and we want to show x equals 0. Now, before I do, I just mentioned I was going to talk about sizes. At least I think I mentioned it. It was in my head to mention it. And let's think about this now. Okay, so what is the size of this matrix? This is just a note because I wanted to mention it was square, but we can definitely think about this. A is n by m. A transpose is m by n. This is m by m. Maybe I'll just put a little box around that. So this is always square. Okay, now back to the proof. We have A transpose AX equals 0. This says that AX is in the kernel of A transpose, right? Because A transpose times AX is 0. But also AX is just by definition, it's in the image of A. Because, and we discussed this, AX is a linear combination of the columns of A. Without a doubt, it's in the image. And so now you see you have AX in here and AX is in here, and they're orthogonal complements. So then AX, I'll write it this way. Because this is the orthogonal complement to the image of A. So now you have a vector that's in a subspace and it's in the orthogonal complement of the same subspace. The only time this happens is if the vector itself is 0. This was one of our properties of orthogonal complements. And so this means X is in the kernel of A, but look, kernel of A is 0. We get X is 0. And this is the end of this proof. So in fact, what we get from this is something quite wonderful. When A has linearly independent columns, this A transpose A is an invertible matrix. So this is my comment number 2. So we showed in this case is invertible, which means you can solve this normal equation equivalently. You can find the least squares solution to AX equals B just by multiplying both sides by the inverse of A transpose A. And when you have linearly independent columns, you will have a unique least squares solution. Now, There's more that's true, and I will just mention this. I'm going to erase this now and let me say one more thing. And then we're going to get back to examples. So I did not want to start with this sort of heavy theory today. I started with example, and then without telling you why anything worked, we just did it. And then we went to discuss why, because that's also quite important, and you will find sort of on the theoretical side questions in your homework or quizzes, exams, things like this in the future. But then we come back to examples at the end, because ultimately this is really the goal of this section. Okay, so one more comment I will make here is that this proof here can be just slightly altered to show generally that the kernel of A transpose A equals the kernel of A. Now that we understand why this works and how it's related to the material we have talked about already in this chapter, we're going to go back to a few examples. Here's the first one. Okay, we have A, we have B, find the least squares solution, and then we will find the error. So let's just start computing. A transpose is like this, and then multiply by A. Okay. We will have a 2 by 2. We get 5 minus 1 minus 1 and 5. Okay? And you know, I can already, if I wanted to, let's figure out the inverse. We will have, and I haven't even found A transpose B yet. I'll do that next. But you see, this is invertible. Although I could have seen that based on our last discussion because the matrix of A has linearly independent columns. Very nice. Well, A transpose A inverse is going to be 1 over 25 minus 1. And then we flip the diagonals, negative of the off diagonals. Okay, very nice. Now we need this vector, A transpose B, which is, here. And here we get 2 and minus 2. Okay, so we'd like to solve. The normal equation is as follows. It is 5 minus 1 minus 1, 5. Say x1, x2 equals 2 minus 2. And because, well, I'll label it because this is it's only our second example and our first since we've actually really discussed what's going on. Here's the normal equation for this system. Okay, but I already found the inverse of this matrix, and so I can solve here for the least squares solution. Maybe I should have called that x star, but in any case, it's fine. So I take, maybe I'll put the 1 over 24. And then multiply by 2 minus 2. Okay, what I have done, I think I mentioned this before, I multiply on both sides by the inverse. And here I just get x1, x2, which I'm writing this way. And over here I get A transpose A inverse, this matrix times this vector. And this is my least squares solution. Now what is this? Well, I have 10 minus 2 is going to be 8 over 24, a third. And then I have 2 minus 10, negative 8 over 24, negative a third. Okay, this is the least squares solution. Here, I'll even put another label, star. But now you see I need to find the error. So part 1, done. Part 2, find the error. So I need to keep none of this on the board. So this part I can now erase once I have found my least squares solution. So what I want is this, the error. Maybe I'll write the word error. It is b, the length of b minus a x star. 1, 0, minus 1. And then here's my matrix A, 2, 0, minus 1, 1, 0, 2. And finally, here is my least squares solution. It's a third minus a third. Okay, just as before, I will multiply matrix times vector, and then I will subtract. Here I get 2 thirds, and then this is minus a third, negative 2 thirds, and we have another negative 2 thirds. This is great, negative 2 thirds. And now finally, I'm going to subtract, then I'll take a length. Okay, okay. The difference of these two vectors, we have a third, we have 2 thirds, and this is minus 1 plus 2 thirds, we have negative a third. Uh-oh, I wrote a half. Now I think we're okay. So it's a square root of 1/9 plus 4/9 plus 1/9, which is the square root of 6 over 3. And this is approximately what? 0.816. Okay. Next example. And there's one letter on the board I want to highlight. I'll make it red. It's this letter. We want to find the least squares solutions, which means not just one. And I never said that there's always just one or anything like this. There's one solution, least squares solution. When the columns of A are literally independent, you just take, as we did in the last example, A transpose A inverse, and multiply both sides, you have the unique solution. On the other hand, if the columns of A are not linearly independent, you're going to have infinitely many least squares solutions. And let's see that in this example. So you notice here, the second column is a multiple of the first column. Without a doubt, the columns are dependent. And you can immediately see just by looking at these that this would be AX equals B would be inconsistent, because if you just put the augmented matrix, you have zeros followed by the 2. Okay, but we go about exact same way as the last example, and it's going to be interesting when we get to error, because we will have infinitely many solutions here. A transpose A equals, okay, we have we have 4, we have 8, we have 8. Here we see A transpose A, and then maybe over here I will write A transpose B. This is 2, 4, 0, 0, 1, 2. In fact, I know what this is before I even take the time to write it. It's 1 times the first column, because the second column is 0. And now, my normal equation, we can write it down for for this AX equals B linear system, the normal equation says 4, 8, 8, 16, x1, x2 equals 2, 4. Now, unlike the last example, this matrix not invertible. Well, this column is 2 times this column, right? It's not invertible, but also we knew that from looking up here. Okay, but we can definitely solve this just how we started the first week of class. We form the augmented matrix and we perform elementary row operations. I'll take a 4th row 1. Then I get 1, I get 2, a half, and then this is still 8, 16, 4, and one more I will do here. I'll just take minus 8, row 1, add it to row 2. I will be in reduced row echelon form after this step. Okay, 0, 0, 0. Okay, infinitely many solutions. Okay, here we go. So x2 is free. Say x2 is t. This is free. Then we get that x1 plus 2, x2 is a half, or equivalently, x1 is 1/2 minus 2t. So my solutions here, I'll even label it with a, here, it's a least square solution is t 1/2 minus 2t. And this is for any t. Scalar. This is why the S that is in red is so important, because you see we have infinitely, this t may be too little. We have infinitely many solutions. Now, I want to make a comment about the error, because this is where we'll realize that in fact every single one of these has the same error. Now let's compute b minus ax star. This is 1, 2 minus 1, 2 minus, now when I multiply, I get 1 minus 4t. Okay, that's this times this, and then I get plus 4t. And then this row times that is just 0. You see, 4t minus 4t, 0. So here, this is 1 minus 1, it's 0, 2. So we have b minus ax star is just 0, 2, no matter what t is. Okay, and so this error, if we want to finish it here, this is just 2. It's the length of this vector here. Okay, now let's do one more, and I want to go back to, we're like going in a big circle today, back to data fitting, which is how we even started the lesson. Let's do this one more example. What you see here, I'm giving you 4 points, and 3 of them sit along the line y equals 0, and then I have 1 that is above at height 2. And we want to use this least squares technique to fit a quadratic polynomial. Okay, well, just as a comment to connect this to things you have done, you likely know my Calculus 2 people, which should be everyone in the class, if I give you 3 points, this determines a quadratic. Just like 2 points determine a line, 3 points in the plane determine a quadratic, and in fact, this is what underlies Simpson's rule in numerical integration. But 4 points, well, particularly these 4 points with 3 of them on a line and 1 other, we're going to have to least squares, find an approximation to fit a quadratic, I should say. Okay, so let's get started now. We'll use this point first. It says y equals 0 when t equals minus 2. So I get the following, not t, c1, excuse me. It says y equals 0 when t is minus 1. It says y is 2 when t is 1. And finally, y is 0 when t is 2. Okay, very nice. So from this linear system, we get our matrix A and our matrix B. Our vector B. Goodness. Okay. A starts here. 1, 1, 1, 1. And then minus 2, minus 1, 1, 2. Okay, last column, we get 4, 1, 1, 4. And my vector B, 0, 0, 2, 0. Okay, so what I'm going to do now, maybe I will, because I want to leave space on the board. As you know, my board is not as large as I would like. I'm going to recopy my polynomial here. And then I'm going to erase this part in blue because I have all of the information already written on the board. Very nice. Now we get started. A transpose A. This is going to be a pretty one. Okay, so the first row becomes the first column. The second row becomes the second column. And then 1, 2, 4. An A. Okay. This will be, as we can see, 3 by 3. Did I leave enough space? Okay, here we go. This is 4. Okay, think about this. Look, minus 2, minus 1, plus 2, 0. Now this one will be something. We have 5 and 5, 10. Okay, but then here, this and this is again, it's the same 2 vectors that I'm taking the dot product of. Now I get another 5 and 5, another 10. Uh-oh. And now I am in 2, 3. I get, look, minus, plus of the exact same thing. Pretty cool, huh? Okay, good. And then, now we just add all of these. We get 10. And then again, here, we get the minus and the plus of the exact same things. And we get, this is going to be 16, 17, 18, and another 16 is 34. This is really cool because you see that column 1 and column 2 are orthogonal. We see column 2 and column 3 are orthogonal. And now I also need, I'll do it over here maybe, A transpose B. This is another one that you can multiply before you even write it down this, because there's only one entry here, so it's going to be 2 times the third column of the matrix. Okay. Now, so our normal equation is this matrix times x equals this vector, right? Should I write that somewhere? Maybe I will. I'll write it in the corner and then I'll be able to erase some things. Now let me write the normal equation here. Four, 0, 10, 0, 10, 0, and 10, 0, 34, x1, x2, x3, or we had them actually C0, C1, C2, and this is equal to this. Now, just with any time you have an this matrix is invertible, you could either find the inverse, or you could make the augmented matrix with this matrix and this vector and solve. I think I'll just do that rather than finding the inverse, although it's really your choice how you go about this. So I am going to now augment, and we will quickly be able to find a solution. We start performing elementary row operations. I'm going to take 1/4 times row 1. And at the same time, okay, you know what? I'm going to do these together. I'm going to take 1/10 times row 2. Okay, because these don't really have anything to do with each other because of how the zeros are placed. So I'm going to do these together. 1, 1, 0, let's see, 5/2 and a half, and then 0, 1, 0, 1/5, and finally this has not changed. Okay, what I need is minus 10 row 1, add it to row 3. I think I have space here. This remains the same. And then we have 0, 0. Multiply this by minus 10, it becomes 25. This is a 9. And then this is -5. This is -3. I'm going to take 1/9 times row 3 and one more. I'm going to take minus 5/2 row 3, add it to row 1. Okay, so this remains the same. This remains the same. And this will be like this, but then this final one, 5/6 plus 1/2. This is 5/6 plus 3/6. This gives me 8/6, or divide both by 2, 4/3. This one is 4/3. And now, well, I didn't necessarily need to keep this normal equation on the board. But you see, we are in reduced row echelon form. We have a unique solution. Let's write our polynomial, and then we will look at the graph, okay? So our polynomial is, so this is the least square solution. Is f of t equals 4/3 plus 1/5 t minus 1/3 t squared. What we're looking at here is these 4 points, if you look here, this one, and this one were the three that were along the line, y equals 0, and then here's the point 1, comma 2. And then the least squares solution to fitting these with a quadratic is here, okay? So I wanted to graph this so we can see. Well, we could go and make little vertical, a bar here and a bar here, here, and here, and calculate the error, for example. But I just wanted to show you, let me zoom in a little bit, graphically, this polynomial that we found, or quadratic that we found, together with these 4 points